Okay, welcome to Lesson 3, Video 2. That's enough of me. Let's get to the stuff. All right, so we're going to look at residual standard error and the sum of squares. The question is, how can we estimate the constant standard deviation? Remember, this is what we said was one of our assumptions about the error random variable. And so how can we estimate that? That's one question. But the other part is variation. Trying to measure and control for variation is the key in statistics and is key as we look at determining whether our model is useful or not. So we've talked about this idea, the total sum of squares and the regression sum of squares and the sum of squares error. Remember that the closer that our residuals are to 0, the better our job is. And so the way we measure that error is taking the residuals and squaring and summing them all up. That's called the sum of square error. Again, it's the percentage or the amount of variation that's not explained or can be attributed to the model relationships. We have n minus the quantity k plus 1 degrees of freedom because we lose k plus 1 degrees of freedom in estimating the k plus 1 coefficients. So just as a reminder of how to tell what are the degrees of freedom, if you have k predictors, your regression sum of squares will be k. So like here we have 7 predictors, and over here will be the 7 degrees of freedom. Now for the total, we have to take n minus 1 degrees of freedom. So over here, you'll have n minus 1 for 33, and then you just take those two difference, and that'll give your degrees of freedom for your sum of squares error. Okay, so this part of the course pack found on page 131, it's upside down. We will get it straightened out here. So again, you've got the sum of squares residuals, you've got the sum of squares total, and the sum of squares regression. Okay. So to get the total sum of squares, the adjusted sum of squares is up here. At sum of squares regression, 136. Then this is the total sum of squares, and so you take this ratio, 136 over 166, you get r squared, which is the proportion of the observed y variation that can be explained by the linear model. Now, unfortunately, there is a problem with r squared. Its value can be inflated by a lot of predictors, and most of those predictors are rather frivolous, so our model is not going to be as useful. So for example, suppose we're trying to estimate the sale price of a house. We could add in things like x6, x7, and 8, the thickness of the potato slab, the thickness of the cutting board in the kitchen, the doorknob on the coat closet, things that really are not going to have some value, but our r square is going to get larger and larger. So the coefficient of determination will get closer to 1 with each predictor we add, but this will not give us a useful model. Therefore, the coefficient of determination is not the ultimate fighter, which I guess they canceled their fights when I'm recording this video. However, it's not the ultimate statistic. A large r squared does not determine a useful model. A large r squared does not determine a useful model. So be aware of that. But just as a reminder, hopefully you made this correction. If SS regression is a large proportion, then the model fits pretty well if the SSE is quote-unquote a small portion. And the model fits the data poorly if the regression is small and the sum of square error is large. We went ahead and calculated the r squared throughout. Now the second part I want to talk about is the residuals. and how the residuals can help us to determine the constant standard deviation that we talked about in our assumptions of the error random variable. So you can find this S on Minitab by just looking over here on your S part. And so this will give you this constant standard error. This is called the residual standard error. There's several estimates you could use, but this is a common one. You can also find this by taking the square root of the mean square error. So over here we have the sum of squares regression. Here we have the sum of squares error, and then the sum of squares total. If you take this 30.446 and divide by 26, you get the mean squared error of 1.171. If you take 136.36 and divide by 7, you get the adjusted mean square error of 19.48. So if you take this adjusted mean squared error of 1.171, which is the sum of squares of residuals divided by 26, that's our numerator, divided by our denominator. Our mean squared error is 1.171. We take that square root, and lo and behold, we get that same S. So that's where you can find it, and that's how you can compute it. Just as a reminder, that's what we're saying here. The square root of MSE also gives you the residual standard error, and that will help us in determining when we're going to use confidence intervals and prediction intervals. Now, I should just point in one more thing for the adjusted R squared. You might have done this homework on Hawks in section 14.2. We're not going to make a big deal out of it, but I just want to show you a quick way that you could do it. If you have the analysis of variance table, all you have to do is take the degrees of freedom from error, multiply it by the sum of squares total, divide that by multiplying these degrees of freedom times this sum of square error. So get 0.2317, subtract it from 1, and you get the R squared adjusted value. Remember, from Hawks, they're not going to do the same sort of model building that we are, so this is sort of a shorter cut way to determine whether you're getting the right model or not. So now our next lessons in 4.6 will be on which predictors can keep, so we can develop a useful model. So be on the lookout for that, and I hope to see you in the next video. Actually, I hope to see you in person too. So until then, and here's my 5th grade intramural basketball trophy, which is my proudest trophy.